Okay, Alessandro, hi. But we are very excited to have you with us, Alessandro. And without further ado, we're just going to switch over to you. I know you've already done your sound and presentation slides check. So if you just want to share your screen with us.
Sure.
I'll give you a 20-minute warning at 12:30, and just by raising my hand. And I wish you very best of luck.
Okay, so thank you very much for the invitation, and really a nice organization and a nice situation, you know. We definitely hope that the future will not about only online interactions, but definitely it's a very good start. So today I'll try to be as quick as possible because I put a lot of things in my presentation. So the general theme of my presentation is about the investigation of the neural building blocks of sensorimotor coordination. But then towards the end of the presentation, I will also give you some slides. I will present some slides about our attempts to develop methods to measure sensorimotor communication. So the first part more about neurophysiology, the second part more, you know, about closer to application. So, so if we start from the very basic, here is something that everyone would agree with: the fact that whenever we move alone, our movements are necessarily the byproducts of individual level sensorimotor loops. We basically have a continuous back and forth of information by sending commands and receiving feedback. And then when we move to the dyadic and also the group level coordination, things get a little bit more messy, because those loops, to control our own movements, actually they have to incorporate, here I just said visual, but it could be other modalities. We have to incorporate other signals that are related to others' movement. And here we can represent some version of how you could imagine the movement of someone else that has to be fed into our loops, sensorimotor loops, to control our own movements. And therefore, we can imagine that during coordination, movements are just the consequences of motor corrections that are ensuing from the visual or the sensory reading of the joint product of self and others' movement. So basically, we have to have the ability to read others' movement. That means that basically we have to extract information out of other movements. But at the same time, we need to be aware that while we're moving, willing or not, we're also writing signals, critical coordinative signals in our movements. So basically, it's all we need to imagine a sensorimotor channel of communication. A little bit more, if we consider that besides reading and writing, there's also a little bit of predictive modeling and also the ability of co-regulate behavior with someone else based on the past history of interaction and the context and so on and so forth, to make things even more complicated than that. Talking about sensorimotor communication, there's this review written together with way smarter people than me and these guys. First author is Pezzulo, trying to set the basic concept of what we believe is sensorimotor communication, which, as I've tried in few words to explain, is actually pretty complicated. We believe that sensorimotor communication is a natural form of communication. It does not require any prior convention or specific code. This is continuous, this is the interesting part, and it's flexible, and it's based on the exchange of bodily signals with or without awareness, as we've seen in the previous presentation as well. And all of this is made to enhance coordination success. Interesting part is that every action can have messages embedded within. So where the neurophysiology starts with this. Obviously, we have to mention mirror neurons. It started like 30 years ago or more. And we know what that means. It means that the motor system, premotor system, is actually conceived in a complete different way, including the ability also of matching sensory and motor features of executed action. Then we have a paper in '95 with transcranial magnetic stimulation showing that we can measure those effects in humans with transcranial magnetic stimulation. We can measure corticospinal excitability's modulation when people are passively observing actions. We made a little bit of story out of it. We already, things have gone on. It's like 20 years. We know a lot of things about this mechanism. And if we want to simplify everything, we can say that human actions are characterized by invariance based on neural constraints, based on biomechanical constraints. Human actions are a kind of stimuli which are particular, for which we probably have a specific neural module to analyze. If we want to use some more engineering terminology, we can imagine that the motor system acts as a classifier or a filter for perceiving specific features of biological motion. And if we want to give a definition, we can imagine that the observer motor programs actually can help constrain an active search of specific sensory features in order to maximize the discrimination between several hypotheses or to support the prediction of future information. It's kind of a Bayesian prior while you have to make sense of a complex environment around you. So the kind of research we run in our lab, we can separate into four different lines, actually 2 lines, action and speech, and 2 approaches, single subject, classical laboratory environment, and multi-agent, the complex situations where you have multiple people engaged in a possibly realistic interaction. We do hyperscanning, but today I will just speak about few studies over here and few studies in the multi-agent section. And first, I start with thanking the people. These are all the people involved in this project. Longtime collaborator Luciano Fadiga. We've been working already like 10 or 12 years together, the postdocs and PhD, and these are the grants. But then let's move to some recent examples of the neurophysiological basis of sensorimotor communication. I don't want to be too long here, but just an example of a very recent paper. In this case, we wanted to investigate the coupling of action and perception at the very basic level. Here we have a classical task where you have a continuous motor control, motor output. So it's an isometric force task, and we're recording electroencephalography. What we're measuring here is one of the classical methods is corticomotor coherence. So the relationship between center and periphery throughout the task. But this time people had to do also a visual task unrelated to the motor task. So they had to detect a stimulus that was a threshold. So basically what we are looking is that the ability of people to actually see the stimulus or not depends on the previous state of the sensorimotor system. So basically what we show is the alpha lagged corticomotor corticoforce coherence actually explains visual perception. In a word, we can say that the intrinsic properties of cortimotor control, so the machinery, the neural machinery that is needed to output a certain amount of force, is actually orchestrating in time if we can see or not a visual unrelated stimulus. To move a little bit higher in the hierarchy of complexity, here it's another very recent example, another study where we have a classical action observation task. There are many, just like the Fadiga 95 paper I mentioned before. People are observing a hand opening or closing action. But this time we changed something. Our subjects were not passively observing. Our subjects were doing either the same action or a different action. This is like the first building block of the interaction. So how the mirror system works when I'm not just observing someone else, but I have to control my own effectors. How that thing works. Because when I'm passively observing, there's a lot of literature saying that there's an increase in corticospinal excitability. Actually, what we show here is that when you have to match your own action, when you have to execute an action, but at the same time you have to observe someone else doing something, basically, I'm not modulating corticospinal excitability, but actually I'm using corticospinal inhibition. So that means that probably motor inhibition is the key neural marker to tease apart what is my own neural needs for moving my body and what are the motor computations I need to implement in order to extract information from someone else. And then another study, another very recent study, imagine these two actions. These two are two different strategies in a continuum of a whole body pointing action. On the left side, we have a safest way where you keep your center of mass projection down between your feet. Basically, you're spending a lot of energy by flexing the knees, but at the same time, you want to be safe. On the right side, instead, you have the other option. You try to save the mechanical energy, but you move you risk a little bit more in terms of postural stability. And basically, this is interesting because these two strategies are equally spread in the population. They're very robust across even years in the same person, are differentiated by the activity of one muscle, the tibialis anterior. So basically, if the whole story of the mirror system was true, was completely true, we would imagine that by observing one of the two actions requiring a strong activation of the tibialis, I would see increase of modulation of the corticospinal excitabilities of my tibialis. Instead, at the group level, this is not the case. And that's why. Because basically, we know that everyone enters in a lab with a specific strategy, with like a personality, a motor strategy to do one particular task. And what we showed that actually the motor excitability doesn't follow what is in the stimulus, but actually follows the difference between me and you. So if I'm a blue strategy person, I'm going to resonate, let me use this term, I'm going to show a greater excitability for the tibialis when I observe someone with the red strategy. And the opposite is also true. So that means that the motor system is actually actively computing a difference between my own strategy and the action that actually I'm observing. So to make a long story short, the three studies I presented show that the ongoing motor control actually changed the way we perceive actions. And this is important to understand the tight and the mechanism, to open a tight and mechanistic window upon action perception loops. At the same time, the second studies is starting to tell us, something interesting. It's telling us that acting and perceiving at the same time changes everything. Mirror-like activities or neurophysiology of interaction cannot be investigated in single subject observing passively stimuli on a screen. And the other one is that the mirror function actually probably computes a difference between own motor template and others' visual appearance of action. This changes quite radically the picture of what is believed, what could be the motor computation during action observation, and what are the implications during the interaction. But it's also interesting because it lets us move from a group level neuroscience to
Alessandro?
Yes, can you see me?
Oh, yeah, for some reason it's just hung. Can you share your screen again, please?
Yes, I do.
My apologies.
Don't worry, don't worry.
Not sure what happened there.
Me neither. Can you see my screen now?
Yeah, perfectly. Go ahead.
Okay, so basically now I was jumping to the second part, trying to translating all those neurophysiological laboratory-like experiments, still trying to make it a little bit more interactive into a condition where it's very hard to do neurophysiology, where you have complex and ecological behavioral co-regulation. I'll jump over this slide because it's a little bit too late. And so we moved to Orchestra and Quartets, because we know already from the previous presentation how these are probably a very nice, interesting model of interpersonal communication, and the sensorimotor communication I tried to briefly sketch at the beginning of my presentation. These are also interesting because offer different degrees of leadership when it's a formal leadership or a more distributed leadership. And there are multiple possibilities to investigate different social structure, if you want. These are one kind of the stimuli we're using recordings we are using in our studies. As you could see, it's a whole body, upper body motion capture of a quartet playing music. And this is the Quartetto Cremonini. It's a Quartetto Cremona, sorry. Quartetto Cremona, it's a world level quartet. These are recordings done together with Casa Paganini, the help of Antonio Camurri and his group, in 2 different European projects, the CMP project and now in Entimement. I briefly sketched some of the results we achieved, but before, a little bit of methods, how we do compute sensorimotor communication. There are so many possible ways of doing it. We are using basically kinematics. In this case, you see a plot of an excerpt of the acceleration profiles, and we used in many of our studies the Granger causality, which is a technique, signal processing technique derived from econometrics to extract the relationship, the cause-effect relationship between 2 time series. Basically, it's based on precedence. So I'm using an autoregression technique, and I'm trying to estimate the future of one signal by using also another signal. If I'm better in estimating the future of the first signal by including information from a second signal, that means that that second signal had something to do with the future of the first one. So it's a technique that has become popular in neurophysiology also to extract the pattern of functional connectivity between neural sources. But we applied it to kinematics and the Orchestra and Quartet scenario. So the first study, already a little bit old, 2012, we recorded 2 conductors and 8 violinists. To make a long story short, we extracted 2 indexes. The first one was the conductor to musician driving force. So basically, we extracted the direction of information from the conductor towards all musicians, and in the first row. And then also the musician to musician, so the cause-effect relationship between all musicians by excluding statistically the contribution of the conductor. So what is the net collaboration, information flow between musicians, removing the conductor? And we did it for the 2 conductors. Here as well, to make a long story short, we had the pieces of music be rated by experts, and we can summarize the fact that in the worst rated performance on technical grounds was that actually had a strong communication from the conductor to the musician, which at the same time was paralleled by strong communication between musicians themselves. Basically, everyone was speaking, no one was listening, we could say. On the other hand, the best performance were when the strength of the conduction actually was paralleled by musicians that were reducing the inter-musician communication. This is a second study, 2014. It's a quartet study with the data I just showed. Here as well, we measured inter-musician communication, which is the total back and forth causality between each musician. And then we summed all this communication, and then the musician driving force. For each musician, we computed how much each musician was causing more than he was caused by everyone else. So then the net positive influence on the other musicians. The music pieces were separated in terms of technical complexity by expert musicians, and as is expected, here are all the takes, the repetitions. In the overall, and also in every piece, in every take, we observed that in the complex scenario, actually inter-musician communication grew. It's possible, it's probably obvious that whenever complexity actually called for more communication, actually that measure was capturing that fact. At the same time, here in the musician driving force, we see that there's a pattern between the 4 components of this quartet, which is relatively constant and consistent across takes, except for take 5, something weird happened. But what is interesting at the overall level, we see that basically there's one musician, the first violin, that was actually always causing more than he was caused. This is telling us that he was the true leader in the group. And then another interesting fact. Actually, we had another condition where the first violin was asked to add to his score some agogic changes, like adding a crescendo, diminuendo, accelerando, and so on and so forth. But he was the only and the sole person in the group knowing the presence of that dynamic change. So that meant that basically we forced him to have more information than everyone else. So basically, we wanted to unbalance the informational content, information distribution within the group. What we saw in the perturbation was that inter-musician communication actually increased in the altered condition, but interestingly enough, the information flow from the first violin to the rest of the group actually was decreased. This could be explained in multiple ways. I have some ideas. Occam Razors to me says that classical musicians, professional musicians, are not happy with this kind of novelties in the way they rehearse. So, but you can tell me later if you have other interesting interpretations. And then the final study, we have the second orchestra, complicated scenario, as you can see, viewed from the top, 30 or 35, I don't remember, musicians on stage. The recording was done only for the conductors and for the first two lines, the two rows of musicians. Here we wanted to extract a little bit more complexity of this interaction, the multi-layer nature of communication. We recorded the head and the hand movements, one for ancillary expressive movements for the torso, the body sway, and the other one, the hand, to measure instrumental movements. Also, at the same time, as was mentioned earlier, we can extract two modes of coordination, because intergroup coordination, it's a kind of complementary coordination. The musicians in first and second line have to do, most often, very different things. Instead, in the intra-group coordination within the line, actually they have to play the same score. So they have to synchronize their movement. Then we did several other analyses and a perturbation here as well. The perturbation is funny because the first line, now they have to rotate 180 degrees, so they no longer see the conductor. Actually, for the first time in their life, they see the second line in the musicians in a face. So now the communication changes completely. So what we see is that there are different effects on different channels. So we see that there is a clear directionality between the conductor and the musicians, and line one in the normal condition drives the music or the movements of the second line, both in the hand and the head. When we apply perturbation, obviously interesting enough, our method capture something that is obvious. The communication pattern between conductor and line one was completely cut, was absent. What is interesting is that the communication between conductor and second line for the head movement was increased, and also the direction actually was reversed between second line and first line. That means that second line now has to increase the communication with the conductor, and now is also the hub of a new communication path from the conductor to the first line. So they're kind of mediating this new rearrangement of the system. Also, in the intragroup, something interesting happened. So the first line that now they have to readjust, they make more use of their peers because they start to synchronize more in both channels, as if they have to regroup and try to rely on peers in order to be able to cope with the new unpredictable, well, they could predict, but the new never experienced situation. At the same time, the conductor, we're using autoregression here, the conductor has to be more clear. So actually it's becoming more repeatable, more readable, because the condition is different. Now has to pass information through the second line to the first line, and it's better off doing something simpler. So these are instead new results, haven't published yet. Julian Laroche is working on this, and soon, hopefully, they'll be out. This is about the intra-body coupling. It's the same data set, and we're working on the first line. So we're saying the first line had to change a lot of things in order to cope with the strange new situation. So, but what is that these people are doing in their body movements? And basically, what we're looking at, the coordination between bow and head. So we want to see if they change the way they reorganize their movement in order to, do what we just seen in the previous results. What we see is an increase in intra-body coupling of movements. You see the plot on the right, it's a cross-correlation plot. What we see is that lags in the cross-correlation doesn't change between the normal in blue and perturbed condition, but the lag variability seems to be lower in the perturbed condition. So that probably means that musicians are making movements between the head and bow movements become more similar, more correlated between them, and also more consistent in the lags. If we look at if we do a power spectrum of the bow movement, what we observe is that something probably obvious is that the frequency content of the bow movements actually show peaks in relevant positions, especially where there is a musical value. And those peaks do not change across conditions. That is probably obvious because musicians were still playing and the score was still followed and read. So they were coping with the rest of the body, but then the bow was still doing the same movement that I expected from the score. But what happened that is interesting in the head? Actually, head movements showed a significant difference between the conditions perturbed in red and normal in blue, but specifically at those frequencies that have musical values. In the normal conditions, the spectrum of the bow, of the head shows actually a lot of energy in the low frequencies, which are basically probably not related to the fine, fast movement of the bow. Instead, when we observe the perturbed condition, we see that the spectrum shows multiple significant periodicity, especially with peaks reflecting half, quarter, and eighth of a note. So that we can simplify and say that probably this data, still working on it, actually is telling us that head movements actually try to rebalance towards higher frequency. So they move the spectrum towards more energy in higher frequencies, trying to match the frequency, the spectral content of bow movements. And to make a long story short and an intermediate conclusion, we could say that there's probably there happening an attempt to coordinate ancillary and instrumental movements to frame and stabilize the timing of the bow movements. And probably in order to replace the loss of timing information that is normally provided by the conductor that I remember they no longer see in the face. So this is all of it. Thank you very much. This is the nice picture I could see from my office if I was at the office.
Thank you so much, Alessandro, for that perfect continuation from what we heard this morning. It's almost as if I planned it. So it was fantastic, actually. Again, to talk a little bit about action perception coupling, as we started talking about with Mark, as we brought that session to a close. The idea being that when we were talking about the first and third row and how they were interacting in their walking, bouncing study. Here again, you're saying that everybody is interconnected. So it's not just about saying, are they synchronous anymore? Now we're saying, why are they synchronous? How those patterns change over time, and how is it related to how they're coupling with different people? I am just checking to make sure that there are no questions coming up on the. Yeah, so we've got no questions up on the YouTube channel yet. I will keep watching those, but I have many questions. I was particularly interested in the fact that you used the analogy reading and writing, which was, I thought, very interesting when you talk about communication. I'd first of all love to hear why you think about it as reading and writing. And then the second is related to that, because reading and writing are both very active signaling processes. Whereas a lot of the times, and obviously the data you've just shown us is very active, right? When I'm a musician and I try and coordinate my bow and head movements, it's a very active signaling that I'm doing. But sometimes the signals that we send to one another are not as active. So one of the questions I sort of had to you, because I'd be curious to hear what you have to say, is what about those other signals, those less actively sent out signals?
Yeah, I completely agree with you. I have to say that sometimes in my presentation I use read and write because I expect very different audiences, and many times I have engineering audiences where usually with the collaboration we have and the projects we have, we talk with roboticists and so on. So the reading and writing, it's an oversimplification and they're easy to understand. But I totally understand that the difference between an active process and what is not active, it's a critical for cognitive, a critical one for cognitive science. And we are into the more active, though not necessarily voluntary kinds of reading, if you want, and writing. We know from studies, we don't have to go back to Jonas in the 70s, showing that biological motion forms a specific shape, but we also know from studies in the 90s that when we are observing biological motion profile and we have to produce another movement which is unrelated to that, actually we see contagion. So that means that although there's no particular need to extract one kind of information we don't have to read properties, kinematic properties of that stimulus, this is actually transferring to the way I'm actually producing movements. So now if we use this continuum, it's even hard to set the separation between what is a completely explicit, voluntary reading actively, and what is, just like an automatic imitation phenomena. And
that sort of leads me on to the question we have on the YouTube live stream from Travis Wiltshire, one of our speakers from later today, who says, "Thank you, Alessandro. Can you elaborate a bit more on this distinction you were making between sensorimotor communication and information transfer? And maybe that is sort of related to what you were just saying."
I think, yeah. Thank you very much for the question. It probably needs a lot of discussion because it really depends on the perspective you're taking. Because I agree that from a cognitive science perspective, it makes a whole lot of a difference. If you take it from the neurophysiological point of view, what I see motor activation when I'm producing a movement. I can measure kinematics, I can measure force, I can measure those things, and I can see effect on the other body. If that is in pure information transfer or sensorimotor communication from the neurophysiological point of view, I think it's a matter of theory that you want to use to interpret the data. But data, it's there to say that there's a change in a system that is mechanically not coupled.
So I think you are probably right. We probably need to have a lot more time to just to dig into that. And in the interest of time, I'm going to have to cut us off there. But maybe you'll join Travis on the chat in the YouTube live stream, and we can follow your train of thought there. So it just leaves me to thank you, Alessandro, for your time, for your talk, for what was very theoretically. I am now thinking about a couple of the things you just mentioned, and